Last time we ended with if you are given the cross-section size and required moment, you could pick out the amount of steel. That's the second step in designing a beam for Flexure. So what we're going to do now is the first step where you already, so we did this. So now what we're going to do is size the beam. And after you have the size, you can do the step we just described, picking the steel. So let's go over how to size the beam. And so where do we begin? There are three unknowns: the size of the beam, B and H, and the amount of steel, AS. And there are two equations. And as we explained earlier, that means there's an infinite number of solutions. Remember, if you had X plus Y plus 3Z equals 1, and this equation here, all you could do is pick a Z. Oh, what am I doing? I'm just so used to doing three equations and three unknowns. So if you had this situation here, you could pick a Z, and then you would have two equations and two unknowns. So you pick a Z, solve for X and Y. Or you could pick an X, any X you want, as long as it's well conditioned, and solve for Y and Z. Or you could pick a Y and then solve for X and Z. Now, there are cases where you could pick certain values, possibly pick certain values, and there's no solution, but that's not what we're talking about. Okay, so you could pick a B, solve for H and AS, okay? You could pick a H and solve for the other two, or pick the area of steel and solve for the size. Okay, what we're gonna do is this. We're gonna pick the percentage of steel, or the ratio of AS to BD, or essentially AS to BH. And so if you wanted to get the smallest possible beam, you would put the most allowable steel, right? So you would pick rho equals rho max. And if you wanted to get the largest possible beam, you would pick rho equals rho min. And to get a practical beam, what would be good, what I found to be practical is right in between, the average. That works out in most cases to be right in the middle, and that'll be practical. And by practical, I mean the steel will fit in the bottom of the beam and those sorts of things. Now, there are situations where you need to have as small as beam as possible. And so what you're gonna do is pick rho max. I don't know why you would want the biggest beam possible, but where rho min comes into play sometimes is for architectural reasons. You'll make a structural member very large, larger than it needs to be. And in that case, there's a minimum amount of steel you will have to have, even though you don't need it all. So here's a procedure. We're going to pick a rho. This is a procedure for designing a beam, not the procedure. There are many ways to do this. This is how I'm teaching my class how to do it. We're gonna pick the percentage of steel, as I just said. We're gonna pick practical or max or something like that. Then, remember how we had this thing where we had MN, RN, rho, AS. From rho, you can get an RN, okay? Before you can get the moment, you have to know the weight of the beam. So you're gonna have to guess, so I guess the estimate is a better word, the self-weight of the beam. Once you have the weight of the beam, you can do a structural analysis and get the factored moment, MU, and get the required MN, which will just be MU over phi. And once you have that, you're gonna be able to calculate the required BD squared, because RN is MN over BD squared. You just calculated that. You got the RN from picking your rho. And once you know how much BD squared you need, you're going to pick out B, H, and D. And so remember the difference between H and D. H is the overall size of the beam, and D is the distance to the steel. And now that you know B and H, you can select the steel in step 2 that we already covered first. So the procedure for designing a beam, once you've selected B, H, and D, you can now get the real self-weight, because you know the size of the beam now. Calculate MU, MN is MU over phi, that's the required MN. And then you do this thing we did earlier. For the MN, you can get the RN, you solve the equation for rho, and then you can get AS. Once you know the AS required, you choose your steel, 4 number 10s, 3 number 11s. And because there's a lot of rounding and there's maybe you might have made a mistake, always double check that phi MN is greater than MU. Now, another way to design the beam is just to pick the size, rough guess the steel, and as long as this is okay, you're fine. Let's do an example. So first, pick a row. I'm going to use halfway between R max and R min, rho max and rho min. And I have a table that you can look up in the textbook, but I've also made a spreadsheet. Okay? And so from the table in the book, the average of these two is 1.07%. And my spreadsheet, it comes out to 1.06%. And the slight difference is because my spreadsheet has been updated to the 2014 ACI code. And you then, for the row, you plug into this equation, and you get Rn is 0.581 KSI. And note that this will always be 581 PSI as long as you have 4 KSI concrete and 60 KSI steel. It's a very common combination. Okay? So it's a good thing to know. 1% steel, about 581 PSI. But you don't have to memorize that because I made a table for you right here. Okay, so here's the table. There's 4,000. This is what I call row halfway. And so that will be, let me pick a different color for the highlighter. That will be right here. Okay, that is the 1.06% in my table. The table in the book, it was based on pre-2014 where epsilon and steel had to be 0.005. And this table is epsilon steel is 0.003 plus epsilon y. And that comes out to 0.0507. Slightly different, so the percentage of steel here is 1.06%, not 1.07%. Okay, and so here's another way to do this. So you find that on the handy spreadsheet. You're going to calculate this. So I've done this so many times. I've made this what I call the super handy spreadsheet here. Okay, so in this spreadsheet, I have, so it's the same thing. So I have row min, row balanced, row max. That's row max. That's row max for this one here. Sorry, that's row max for a column, and that's row max if it's acting as a beam. Okay. Some people just like to use half of the max. I like to use the average of max and min, and there it is. Okay, 1.06%. But what I've also done in this spreadsheet, you see this Rn equation here? That Rn equation is just a function of rho, Fy, and m, which is a function of F prime C. So in the spreadsheet, the super handy spreadsheet, what I realized is, oh, I know F prime C, I know Fy, and then when you download the spreadsheet, I hide that column. There's no need for you to see that, but I need those numbers for the spreadsheet to work. And so what I've done for every row, I've calculated the RN for it in PSI. So you don't even have to do that calculation. So what you do, to start the problem, you go, oh, I want F prime C is 4,000. I want grade 60. And this is your choice, but I'm going to pick halfway between max and min. And that's my row and my RN. So you don't even have to calculate RN. You just have to read it off, 578 PSI. And so that's where this comes from. So for the super handy spreadsheet, all you do is you pick your F prime C and Fy. You come here and you go like, oh, 1.06%. Oh, let me try that again. 1.06% and 578 for RN. There you go. Let's continue. So here's the problem, and I'm just going to write over here. Oh, rho is 1.06%. RN is 578 PSI because we've picked the concrete and steel. So you were given the live load, the dead load, but not the self weight. And so 2 ways to do it. Just take 10% of the total load. So 1.5, so 10% of that is 0.15 kip per foot. Or you can estimate the size of the beam as 1/10 to 1/12 the depth, and then half of the depth is the height. So 20 feet, I can't divide that by 12. I guess I could. That'd be 20 inches. 20 feet divided by 12 is 20 inches. But I'm gonna just do 20 feet over 10 is 2 feet. And half of that is 1 foot. And so that's 2 square feet. And concrete is about 150 pounds per cubic feet. So that's an estimate. So it's just a guess. It's somewhere between 0.15, 0.3 kip per foot. You can take 0.2. Oh, and I just said that, but that's actually what I did. So 0.2 kip per feet. And I'm just going to do live, WL squared over 8. That's only because it's simply supported. If you have something like this, you have to do a structural analysis and get the moment diagram and get all the moments. But in this case, it's just WL squared over 8. Live, the dead load, total dead load is 0.5 applied, 0.2 self-weight, so 0.7. And you get 35, and the combination, 1.2 dead, 1.6 live, you get 122 kip feet if the beam weighs 0.2 kips per foot, which we don't know until we get the size of the beam. And so if we're lucky, the beam comes out to be 2 feet by 1 foot, and we don't have to redo this. But I'm guessing that the beam will not be that size, and we'll have to redo this. Okay, so we need 122 foot kips is MU. So we need, so remember phi MN greater than MU. So MN has to be greater than MU over phi. So the minimum MN required is 122 over 0.9. And we're going to do everything in kips and inches. So I multiply that by 12. So MN is 1627 kip inches. That's how much moment we need to do. And what we're going to try and do is get a beam size so that the percentage of steel comes out to 1.06%. Okay, so RN, we just looked it up, right? It was 578 KSI, PSI, so 0.578 KSI. MN was 627. So remember, RN is MN over BD squared. So BD squared is just MN over RN. And so we need 2,815 cubic inches of BD squared. And so just be careful. If your moment was in kip inches, your RN has to be in KSI. If your moment was in pound inches, then you would use 578 PSI, okay? Okay, so I'm gonna write the number down here. 2815 is what we need for BD squared. Now, this is ridiculous. You could have D of 1 inch and B is 2,815 inches. That's just ridiculous. Or I don't know, you could have B as 1 inch and D would be the square root of 2,815. What we want to do is do something practical. And so we're going to control the aspect ratio. So there's B and H and D. So D divided by B. The beams are usually deeper than they are wide. We want D over B to be 1.5 to 2. And so 1.5 is wide. So let's say there's 1, 1.5. There's 1, 1, 2. Okay, so that's 1.5, and that's 2 for D by B. Okay, so 1.5 is towards the wider side, 2 is towards the skinny side. I'm always worried the steel won't fit when we get all done, so I tend to choose the 1.5, but it's up to you. And so BD squared, so I'm going to do 1.5B for D squared, and that has to equal 2815. And so don't forget that 1.5B squared is 1.5 squared B squared. And I've done this so many times. 1.5 squared is 2.25. Okay, and then so you'll end up with B cubed is 2815 over that 1.5 squared, 1251 inch cube. Take the cubed root. Everyone has a calculator. 10.8 inches. So I'm going to round it. This example is 11, but I just think it's weird. You just should have, plus we already guessed it was 12 inches wide, but I probably would have, in hindsight, gone with 12 inches as the width, but I didn't want to redo the calculation, so I did 11. So again, if it was me, I would just round that up to 12. Okay, especially if you rounded it to 12. So you might go, oh, B is 11 and D is 1.5 times 11. That's not going to work because B for the equation to work was 10.8. That's pretty close. But if you rounded it up to B equals 12, D is definitely not going to be 18, 1.5, because you've messed up the B, you rounded it. So in any case, what I want to do and what I want you to do is whatever you round the B to, put it back into here. Oops, that's supposed to be 2815. 2815, I'm sorry. And so D, oh my, so this is probably wrong. D is, let me get my calculator out. That 2844 was from the 1.07%, and I updated this thing to the 1.06%. Anyway, 2815 divided by 11, take the square root of that. Oh, I did something wrong. 2815 divided by 11, take the square root of that is 16.0 inches. Oh, I lucked out. It's about the same. And so add 2.5 to that. So 18.5 inches. So I'm going to round it to 20. So good. 11 by 20. Now, if I was doing this again, what I would really do, I would make it 12. 12D squared, 2815. So let's try that. As long as I've messed this up and we're doing it again. 2815 divided by 12. Oh, 15.3 inches. I'm going to add 2.5 to that. H is 17.8 inches. So 12 by 18 inches would probably be a better beam. We'll see. But anyway, we're going to do 11 by 20 inches. So this is an example of either of these would have worked, and it'd be fine. It's an example of how there are many solutions to this. Now that I'm redoing it, I think I prefer that. It's just way easier to build something that's 12 inches by 18 inches than 11 by 20. And then you can do the rest. Okay, so that's how to size the beam. Just a comment, on these little mistakes that you see as I go through. That's just how I really do these problems. I don't always get, in fact, I almost never get them right the first time through, and I'm always checking and redoing it. But typically, when I write out a solution, I only put the final nice solution, and you get the impression that, oh, you can solve these problems perfect right through with no mistakes the first time. But this is really how things go. There's always mistakes. You fix them, you redo them, and then you get it right. Okay, so that's that. You now know how to size the beam. You know how to pick out the steel. What's left is we have to decide how long the bars will be. Where do we cut them off? And that's for another day. But what I think we'll do next is we'll do another example from start to finish in the correct order. So we'll size the beam, then we'll pick the steel, and we'll do all that, and then we'll check everything at the end. And that is really your next homework, is to design the beam for Flexure. Okay, so stay tuned for an example that will come next. So I always think it's funny that you get to see me close the Zoom meeting off. I should really delete them, but I've gotten used to you seeing this. I'm too lazy to edit it out. And it's funny. It's like you get to see somebody that thinks they've turned off their self-recording, but it keeps going, and you see what they're like after the recording's over. Anyway, next video will be design example.